Hello, everyone, and welcome to this No Fluff, Just Stuff presentation on migration engineering with OpenRewrite. I am Sam Snyder, VP of Engineering at Moderne. I work on our core refactoring technology that you guys know as OpenRewrite. And to begin, I think we'll just briefly discuss what I mean by migration engineering. Migration engineering is what you're doing whenever you're working on a cross-cutting concern across all of the classes in your repository or all of the repositories in your organization. Whenever you need to make some small uplift or upgrade everywhere, we're talking migration engineering. And this is something that can be remarkably tedious to do without automation. In my own past, when I was at another company, I got tired of some of our developer tools being a little bit out of date. In particular, we were using a very old version of check style, and for some reason, I decided to take the initiative to upgrade to a more current version of check style. And when I did that, I found that the bug fixes in check style that had been made since the old version we were on and the new version we came to meant that even for the exact same set of rules, there were hundreds of new failures detected in the existing projects. And so I was doggedly stubborn and I slogged through and eventually committed changes that affected 5 to 6,000 files in one long go. And that was such a tedious and arduous process that thereafter I promised myself that never again would I make the mistake of upgrading something like check style, of doing that form of what I would now call migration engineering. But really, the problem is that I attempted to do that manually. And today, with OpenRewrite, I could have done that much more tractably. I could have written recipes to automate the uplift of many of those failures, and I could have made it much easier on myself. But at that time, OpenRewrite didn't exist, or in the form it did exist as a tool at Netflix that Moderne co-founder Jonathan Schneider had not yet open sourced. I had no access to it. So how can OpenRewrite be used to automate these kinds of migrations, right? How to automate it when you have a new security vulnerability pops up in industry and you need to upgrade, the dependencies of all of your 10,000 repositories to one that isn't vulnerable, or a new version of Spring or some library you use has come out and the old method invocation needs to be replaced with the new method invocation, or all of your software stops working. That is migration engineering, and that is stuff that we can automate with Moderne and with OpenRewrite. So I'll go ahead and share my screen, and we'll start giving some examples of what I'm talking about and how to kind of get into it. So OpenRewrite, free and open source, Apache 2 licensed core of parsers and recipes. And a parser produces an LST, and a recipe makes changes to that LST, and these are ultimately written back to source code to automate patching your source code in some respect. And we'll define and get into these terms in a little bit more detail as I continue on. But to maybe begin with, to make some of this concrete, let's run a few recipes. And this is the Moderne hosted SaaS application, which is a place where you can run OpenRewrite refactoring recipes on any of the 37,000 projects that we have ingested from public GitHub repositories. And when I say you can do this, I mean it. Anyone with a GitHub account can, or a Bitbucket Cloud account for that matter, can log in and start running recipes on these public repositories. And so I have selected here a subset of that 37,000, which are 150 or so well-known Spring repositories. So, let's run one recipe to see kind of an example of what recipes do and how and kind of how they make changes. This is our common static analysis recipe. which is from, if we look at the view recipe source, this comes from the rewrite static analysis project, which is like all of our recipe modules and the core parsers that enable this transformation, open source on GitHub. And I'm just going to go ahead and kick this recipe off. And while that starts running, I will point out that this is a collection, an aggregation of other recipes. And we see here that this has some, I don't know, several dozen at least different fixes for common static analysis issues, things that a linter, your sonar cubes, your spot bugs, your covariates, your what have you, would complain about in your source code. And these kinds of static analysis tools, well, they often provide valuable insights into anti-patterns or other mistakes you're making, often have driven me crazy. I remember going back to my check style example, I decided I, on a personal level, hated check style very early on when I received an error that an error that, on line 350 on column 47, I had missed a space between my if statement and the opening parenthesis of its predicate. And I was like, if you know so well where the space should go, why are you failing my build? Just put the space there, man. Like how hard can it be? Well, now that I've worked on a lot of parsers for OpenRewrite and dealt a lot with the complexities of your context-free grammars and all of that, I understand better now why it was difficult for check style, but also what the reasonable successor to tools such as that might look like. And that is a system that actually does just make the change for you rather than adding another item to your already overflowing to-do list. Just fix it. So, I've now run here this common static analysis issues on this selection of repositories. And if we click into any one, we see the kinds of changes that this recipe is suggesting. It's suggesting things like, lowercasing this variable name to follow a pattern because this guy is not a static final variable, or things like, renaming these to be camel case because this is Java, not Python. And other little things like that. So, you might consider it a migration engineering type task to improve code quality or to get all of your code following a single standard within your organization, because again, that is a cross-cutting concern. Whenever you have cross-cutting across all of your code or all of your repositories, or even just a substantial subset of it, you're now engaged in migration engineering, right? None of the changes that are being proposed here are really about what this code is doing. They're about how it is packaged, the conventions it follows. And there are many other kind of considerations that are similarly cross-cutting. Things like, cancel this recipe run. You've gotten enough out of it. Things like, upgrade to Java 21, for example. And so much like the common static analysis recipe was made of an aggregation of other recipes, the upgrade to Java 21 recipe, and I'll go ahead and kick this off. The upgrade to Java 21 recipe is made out of a collection of other recipes that that together contribute to producing the effects that we'll see in the diffs. And this kind of highlights that this is not AI. This is a rules-based system. These are all small programs written by human programmers to achieve some result. And that is a component of how they can be precise and accurate with their changes, bugs notwithstanding. I mean, any program written by human hands can have bugs in it. But the nice thing about automation is that once you fix that bug, you just run the recipe again and you get your improved result. So we pop over here, start looking at results, and we, would see in here a mixture of all the different kinds of things that might be necessary to affect this sort of Java migration. Things like updating dependency versions or adding dependencies in the case of like the Jakarta stuff when stuff may have moved out of Java X and into Jakarta. Things like updating build files in addition to upgrading the version of Gradle that is in use. Yeah, upgrading for 7.6 to 8.5. And then so the necessary stuff, the collateral around the code, as well as the code changes, because as human programmers, when we're talking about doing migration engineering, we're often talking about not just the code, but all of the stuff that comes with the code in order to contextualize it and build it and distribute it and package it and all of these things that are not just the code itself. If you want to get a migration done, you need to be able to touch data files. You need to be able to touch Gradle wrappers and properties and all of these other things. And recipes are capable of doing that. And so, when we get to the code changes, we would see both the absolutely necessary things being done, as well as changes to take advantage of new functionality, things like replacing get zero with get first. Things like, let's see if we have any text blocks, maybe not in this one, but things like taking advantage of Java 17's allowing you to have text blocks rather than multi-line strings. Yeah, here we go. Here's an example of that. Yeah, replacing this guy with an equivalent text block. And so everything I've shown you just now, I've happened to run through this Sass interface, but you can equally run any of these recipes with our open source Rewrite Gradle plugin and Rewrite Maven plugin directly on your Gradle and Maven builds. So I'm showing the Sass because it demos better, it looks nicer, but be aware that you are not required to use the Moderne Sass in order to run any of these recipes, nor does the recipe execution process inherently call out to any third-party service or any server of ours. So yeah. So now, so as we've kind of looked at this like migrate to Java 21 recipe, and I've pointed out how it'll do some dependency updates and is an aggregation of smaller recipes that each affect individual parts of this migration, you might think, okay, this is great, but at my organization, I know that when we're upgrading, to Java 17 or Java 21 or whatever it is, I'm also going to need to upgrade the version of our parent POM to the new version of the parent POM that includes the various settings that we want to have. And I need to upgrade the version of, my company core lib from 1 to 2, as that's the version that's compatible with Java 17. And so the organizations I find who are very successful at leveraging automation to affect migration engineering and get these sorts of big lifts done are those that will take these open source recipes. Let me just make sure this is clear. Yeah, they'll take like these open source recipes and start adding into them the things that are specific to their organization. So, I'm going to just click this add to builder button to start off with, add upgrade to Java 17 to what we call a declarative or a YAML-based recipe, where anytime you want a recipe that is just an aggregation of other recipes with various values filled in, the YAML recipe format is the first and most convenient place to go for that. And so, if I needed to say, okay, I want to do the off-the-shelf upgrade to Java 17 and also, upgrade a Maven parent POM, I could, let's see, upgrade Maven parent project version. I could say that, org.mycompany to fill in the values that are appropriate for my organization, add that to the builder, maybe do similarly an upgrade dependency version sort of thing for some internal library, and add various customizations or layer on top additional changes to the off-the-shelf open source stuff for anything proprietary. And then I could say to my friends and colleagues, hey, run our customized upgrade recipe. Don't, the off-the-shelf one is great, but I've added additional stuff for our organization into this. And through doing that, you can kind of very quickly take big chunks out of a migration, right? All the tedious, repetitive, mechanical parts of getting to the latest version of whatever it is are things that are potentially subject to automation. And even if this upgrade, this migration recipe might not get you 100% of the way there, it'll take off all of the mechanical bits, all of the parts that are repeatable, and leave only the things for which a human engineer really needs to consider deliberately what is the appropriate replacement for the thing I was doing before, right? We're moving to JUnit 4 to 5, and I've got a custom rule that has no direct JUnit 5 equivalent. Like, that might not be subject to automation right away. Someone has to make a decision about what to do. Okay. And, so there are some 2,500, I want to say. Let's go back here. Yeah, a little over 2,500 recipes in this catalog, but that covers a lot of useful things, and it primarily starts in the Java ecosystem, although new kind of data formats as well as programming languages are coming online all the time. We're looking forward to the first version of our C# support really coming out here soon. And so there's a lot in here, but the ocean of software engineering is both wide and deep, and this really only scratches the surface in many areas. So it's not too hard to come to a place where you're like, well, I have a migration engineering scenario. There's something I want to change across all of our recipes, or not all of our recipes, all of our code, and there's no existing recipe for it. And even assembling the off-the-shelf recipes together uh, in the YAML format is not cutting it. I need to go deeper. Well, you've come to the right presentation, because in today's session, we're going to talk about how to begin wrapping your head around custom recipe authoring. And in part 2 of this workshop, we will get into more of the details and more of the advanced functionality that is available to recipe authors. So before we can kind of get into how to write your own recipes, we need to understand some fundamentals about what we're talking about. And so this is the docs at openrewrite.org, has all of the documentation that we've put out for OpenRewrite, the stuff on running recipes and the stuff on authoring recipes. And what we're going to start with is some of the key kind of concepts and explanations of how this technology works. Because once you're progressing from being someone who is assembling off-the-shelf recipes together and treating them as a black box to someone who wants to write one of your own, you need to start understanding these things. And nothing is more fundamental to understanding the nature of recipes and recipe execution and migration engineering than what we call the LST. As programmers, we are all deeply familiar with the text-based representation of code. We write it, we read it, we interact with it every day, but it is not very suitable for automation, right? Maybe you've tried to craft the perfect regular expression to update code and found that if not maddening, then substantially and sufficiently inaccurate that you couldn't run it over a large code base and commit the results with confidence without going and checking every single change it made individually. And the difficulty of manipulating text programmatically, well, not just of manipulating text, but of manipulating text that happens to represent computer programs programmatically, contributes to what I think of as a great irony of software development, that we are professional automators, that what we do is automate stuff, automate processes, automate transformation and manipulation of information, and yet the information formats that we work with have been code have been substantially immune to automation in many respects throughout the history of software development. And so we need a more structured representation than text to make it addressable by programs in a sane and reliable way. And so the next step on top of the next most structured kind of representation of code is the abstract syntax tree. The internal. If you ever looked inside a compiler or took a compiler's class or a parsing class in school, you may have already be familiar with this term. An abstract syntax tree is a structured hierarchical representation of code internal to many a compiler. And but a compiler's purpose in generating an AST and operating on it is to generate bytecode. So the compiler internal abstract syntax tree for Java or other languages has often already stripped away many of the niceties of the textual representation, things like the formatting, the white space, the comments. And that's fine if you're generating bytecode because none of that is relevant to bytecode. But we're trying to manipulate this structure and then generate source code again. And on a very human level, even if you produced a technically correct change list or a technically correct patch file, the person reviewing your code is not going to accept that pull request if all of their formatting got clobbered and all of their comments got stripped out. So on top of the compiler abstract syntax tree, we bring back in all of the formatting, all of the comments, all of the stuff necessary for it to be a lossless representation of code. And indeed, we originally just called our representation an abstract syntax tree as well, as it wasn't, aside from that, initially too far divorced from the compiler internal abstract syntax tree until someone kind of snarkily said to us one day, well, not very abstract anymore, is it? And like, well, fair point. And so we probably could have called it like a concrete syntax tree, but we wanted to emphasize that it's not just syntax we're talking about here, because on top of just the syntax and the white space and formatting, we're also, and this is crucial, including all of the type attribution. So that in LST, you can tell the difference between a log.info call that is being directed to slf4j and a log.info call that's being directed to log4j, something that even the most perfectly crafted of regular expression could not differentiate on its own. And so in addition to the type attribution, the LST format includes other valuable metadata that a programmer would want to consider when attempting to manipulate things programmatically. Things like what's on the class path, what dependencies does this project take, what versions are they, what version of Java was this built to target? All of this, what version of Gradle or Maven was used? All these things that a human programmer knows about and can consider when making changes has to be included in the LST model in order to be addressable by recipes. And I've been using this term recipe a lot, so it's probably time to define it. And it's pretty straightforward. The idea of a recipe is basically just any program that manipulates an LST as a recipe. And we have a standardized interface for this that I'll show you, but that's all I'm talking about here. Cool. So when you are moving beyond just snapping YAML recipes together and wanting to or needing to create an original recipe of your own design, you've wrapped your head around the basic concept of an LST. Now you need to get more specific. You need to understand the LST format of the language you were looking to manipulate. And for most of our programming languages, they all are represented by the JLST, short for Java, with some language-specific extensions. So in order for you to kind of transition from or adapt your knowledge as a human programmer who operates on the text-based representation of code to a migration engineer who can operate on more structured representations of code like the LST, you have to be able to kind of mentally translate in your mind between a text-based representation and the LST representation. And so we have this Java LST examples page in the documentation to try and help you surmount that particular part of the learning curve. And so if we look at this diagram from near the top of the document, we will see a demonstration of an LST. In the dark box above, there is the code that is represented by the LST fragment that is in blue beneath it. So at the top level, the entire program is collectively represented as a j.compilation unit, which has kind of three interesting fields, the package declaration, a list of imports, and a list of classes. And each of these is kind of recursively defined in chunks that start big and get small as you get down into the details. So, an import is made out of a j.import, which is made out of the import keyword, and the j.field access data structure and a field access is made out of another field access, down until just the individual identifiers for, Java util and array list. And if we look at the class declarations, well, that's just the part of the file that doesn't include, the package and the imports. And a class declaration is made out of, some modifiers and a name for the class, which is represented as a j.identifier, and the body of the class is inside of a j.block. A j.block is primarily a list of statements, in this case two, one which is a variable j.variable declaration for list of integer a, and one for this int first method, and so on and so forth. So you get down to the very smallest parts. And in this document, we also kind of give examples of each of the kind of Java LST elements, showing that a binary is an operation where two other symbols are combined or two other expressions are combined by an infix function, such as addition or string concatenation, so on and so forth, with class declarations, method invocations, all of that good stuff. And so once you've kind of like, okay, I've got a sense of what a Java LST is like, how do I actually go about manipulating these things? How do I write a recipe? That's where it starts to become important to understand the visitor pattern. And the visitor pattern is not an invention of Moderne or of OpenRewrite. It is one of those original like Gang of Four design patterns that transcends any individual programming language. And you may already be intimately familiar with these, or you may have never touched one even in a long career. And what that really often comes down to, at least, is what kind of data structures is the code you author working with? Like if you are operating on lists and maps and some of these more straightforward or kind of one or two-dimensional data structures, it is sufficient to use iteration and such to traverse them and make sense of them. And when you have a more complex data structure like a tree or a graph, you may find that the details of traversal, when intermixed with your actual business logic, the transformations you want to make for a mess of unreadable code. So the visitor pattern was invented to kind of create an abstraction to separate traversal of the data structure from manipulation of the data structure, and kind of allows you to interpret or to perceive a tree or graph as a linear sequence of events, such that you can kind of register for just the events you are interested in seeing. And there's a lot of kind of detail about this in this document that you can go and peruse at your leisure. But that's kind of the key insight. Whereas if you just have the raw LST for a class, it's complex and it's complicated, and just saying you have a recipe where you're like, well, all I want to change is method invocations. A visitor pattern lets you do that. It lets you say, I just want to see all of the method invocations in the document, and just traverse through everything else and just let me look at method invocations. And so when you're writing an OpenRewrite recipe, visitors that visit each of the LST elements are substantially the thing that you are working with on an ongoing basis. So let's get into some custom recipe authoring. At least understanding the anatomy of an existing recipe so that you will be well prepared to write your own at some point. So if we go to not app.moderne.io, rewrite recipe starter. So we have this repository set up, which is an example recipe module, where we have build files for both Gradle and Maven, so that you could kind of clone this template into your organization, delete the build files of whatever build tool you don't personally prefer, or whatever build tool your organization does not prefer, and then can get into writing recipes directly. And all of the recipes that are deployed in this app.moderne.io tenant are recipe modules just like this one. It's just a jar that is built and published that happens to contain recipes in it, as opposed to a jar that contains anything else. So kind of going back to this example of this like YAML recipe I put together to customize the upgrade to the Java upgrade recipe with a specific upgrade parent version for my company. The you could copy and paste this YAML around and say, hey, everyone, stick this YAML into your project, tell the OpenRewrite build plugin to run it, and that would work, but it's not particularly durable, right? It's not if there's something important to our organization, like if migration engineering is a real discipline, then you need to treat it with the same discipline as any other form or subdiscipline of software engineering, and be putting it in a repository with tests and with with some degree of review and durability, so that it doesn't just get lost in your Slack message history. Okay, so here I've cloned down the rewrite recipe starter repository and opened it up in IntelliJ. And so, if you have a YAML recipe that you want to save and distribute throughout your organization, then within a recipe module, if you put under, source main, resources, meta inf rewrite, some YAML files, my Java migration.yaml, then any YAML you stick in here will be interpreted when OpenRewrite loads the recipe module and check to see if it contains a recipe, and if it does, it'll be made available exactly the same as a recipe written in Java or any other JVM language would be. And as of IntelliJ 2024.1 Ultimate Edition, they have started to build in. See if I can get it to, yeah, there we go. IntelliJ and JetBrains have started to build in support for the OpenRewrite YAML format. So when you're editing a rewrite YAML, it can help you with autocorrect of all of the kind of recipes that are available on your class path, so that you can easily, Java. I was talking earlier about, adding dependencies. So you can easily say, well, I want to add a dependency, and it can prompt you that, group ID and artifact ID are some of the required fields there. Org.mycompany, etc. And so this can be a great way to assemble and edit OpenRewrite recipes, particularly if you're not using the recipe builder in the Moderne SaaS. Okay, cool. So that is kind of how you store and manipulate a YAML recipe. Let's start getting into how you operate on a more something more involved, like you just do something off the shelf. The first example for getting a little bit deeper is to use refaster templates. And this is a technology that came out of Google, I believe, that that lets you have this like annotation processor based like kind of templating mechanism in order to write, find and replace in a kind of pattern matching based way, that where this Boolean expression is potentially any Boolean expression that kind of fits this shape will be whatever's in the before template will be replaced with whatever's in the after template. And for example, in this simplified ternary test, this is a unit test which is going to run this recipe on a bunch of expressions that can be simplified, and assert that this block of code will be presented to the simplified ternary recipe and be turned into this substantially simpler version. And this kind of way of writing recipes is very straightforward. It's very easy to understand and can do some cool stuff, but it has some limitations. And substantially, its limitation is that it is limited to manipulating expressions. And expressions are, within the Java grammar, are things that return a value. Or rather, you're kind of, I guess it can manipulate some statements. You're kind of limited to changing things within a class declaration, within a method declaration. I don't think that this can deal with annotations, for example. It cannot add a whole new method declaration, for example. So if you're trying to do something that is kind of within a single line or within a few lines, these refaster template, and you don't need that much context around it, that a simple pattern match, like this is kind of like a super powerful find and replace. So if you're just doing a find and replace type operation, a refaster template can be a very accessible way to go about that. But what when you need to go a little bit deeper, right? If you need to go into something that you cannot easily construe in this way, or you might need to do some additional stuff like manipulate imports, right? You want to add a new symbol to a class. Well, that's where you need to get into a visitor-based refactoring recipe. And this is kind of the lowest imperative level of recipes. And we'll kind of start with more or less the rest of this presentation will be me explaining how this assert equals to assert that recipe works so that you are equipped with enough knowledge to read and make sense of recipes that currently exist, which will let you be well set up to write your own. And in the next version of this class, or in migration engineering part 2, next session of which I'm giving tomorrow on Friday, we will live code some recipes. So I find that the easiest way to understand most pieces of code is not, at least initially, to look at the code itself, but to go to the relevant tests where you can see the code operating in its intended context, producing its intended values. And so if we go to the tests for this assert equals to assert that recipe, we see that the test implements this rewrite test interface, which makes available a few utilities for testing recipes, such as this defaults method, which lets you configure, unless subsequently overridden, configuration that's common to all of the rewrite run invocations within the class. Things like saying, this is the recipe we're going to use, and this is the Java parser we're going to use to turn the before segments of text into the LSTs the recipe operates on. And we'll come back to that in just a second. And so then we get into a unit test, which is using this rewrite run function to invoke OpenRewrite and to invoke the configured recipe. And this guy accepts a variadic number of assertions that take the form of a before. This a before will be transformed by this recipe into this after. So this test is saying that assert equals to assert that is going to visit the LST element parsed from this text, convert it into a different LST that when printed back out to text will look like this. And so even without looking at a single line of code within the recipe itself, we can see that what this guy's going to do is visit the JUnit5 assertions class and replace it with an equivalent assert_j assertion. So we're going to move JUnit5 assertions assert equals to assert_j, assert that is equal to. So we're going to visit a single method invocation and replace it with a chain of 2 method invocations. And that will be what this recipe does. So now that we have a sense of what the recipe is going to do and how these tests operate, well, let's see. Let's go ahead and run this test. Make sure that everything's in good working order. There we go. Test passes. The recipe did what it was supposed to. So this recipe is currently in good working order. So we pop over to the recipe itself, and we see right at the top that we're using some Lombok annotations here in order to assert that this recipe is a stateless and immutable value class. Using Lombok with OpenRewrite is not obligatory, but we do find it to be convenient for making recipe definitions terse and easy to understand. So throughout the OpenRewrite codebase, you'll see a decent amount of usage of Lombok, although it is a sad limitation that our own Java parser does not itself understand Lombok annotations. So that's a long-standing thing that I have wanted to add. And that just means that methods generated from Lombok annotations will not be type attributed when parsed by the OpenRewrite Java parser. Maybe one day. So anyway, to implement assert equals to assert that, it extends the recipe class. And this has a few human readable prompts the person overwriting recipe to return some human readable descriptions, a human readable display name, and a human readable description. And each of these are interpreted as markdown. So, in any context, such as the Moderne SAS, where this recipe's name is going to be displayed or described, you can use Markdown in order to tell it to format things like code with backticks is the most common usage of that. Okay, and after essentially the recipe metadata, we get down into the visitor, which is the meat and potatoes, the heart, the beating heart of the recipe, the part that actually does something. So right out the right out the rip, right out the gate, we see that we are returning a new instance of a recipe, or not a new instance of a recipe, a new instance of a visitor. Visitors recipes are immutable and stateless. Visitors are allowed to be stateful, to have state as they traverse through an LST, but each visitor is going to see an LST representing, every source file in the repository, and it should not leak state between those visits of source files. So the contract of the get visitor method is that every time it is invoked, it will return a new instance of its visitor, not a cached instance. So you will never see in one of our OpenRewrite recipes in open source a cached result being returned from get visitor. So don't you make that mistake either. And then the very first method invocation in here is one to preconditions.check. And preconditions.check is a function that takes in two visitors and combines them and returns a single visitor. And what this does specifically is essentially a performance optimization, right? A visitor traversing through a file that it does not need to make any changes to is just wasted time, right? It's wasted compute. And traversing through LSTs needlessly waste time. So if there is a quick and efficient check that can be made to rule out files that are obviously going to be irrelevant, that will definitely not be changed by the recipe, you can use a precondition to make sure that your recipe wastes as little time and compute as possible on irrelevant files. So in this case, the purpose of this recipe is to transform JUnit Jupyter assertions into assert J assertions. So this precondition says, hey, only apply the second visitor, the one that actually does stuff, to an LST if that LST has the JUnit Jupyter assertions class in use. And again, these visitors, these recipes are going to see every single source file in every repository that you run it on. So it is kind of the first responsibility of a recipe to avoid making changes when it should not. Because even a project that uses JUnit Jupyter assertions extensively, it's still going to be a small minority of all the method invocations that are in the project. And so it is both ideal for performance to quickly skip irrelevant LSTs and essential for correctness to always remember, there's stuff this visitor isn't going to change. It's a mistake that first-time recipe authors sometimes make, that they get into overriding visit method invocation or whatever and immediately start changing stuff. And it's like, oh, hold on, you're going to change too much. You should have a very defensive style of programming when operating on LSTs programmatically. So this this uses type essentially is a performance optimization. This recipe would still functionally be the same. If we removed it, it would just run slower in practice. Okay. So, oops. So, if we get into this Java ISO visitor here, then if we're actually hitting a breakpoint in here, this uses type predicate will already have been evaluated kind of successfully. Okay, so we know from looking at the test that what we're going to do is replace assertions assert equals with assert J, assert that is equal to. And that means that if you remember what I was saying about visitors, that the type of thing we are interested in visiting is method invocations. And so we new up a Java visitor and we override visit method invocations because everything else can be left the same. That's method invocations are what we want to transform. We're not changing class declarations. We're not changing binary expressions. We're just changing method invocations. So the visitor pattern lets us focus on the thing we're interested in and ignore anything we're not. Okay, and so the very first method that is called by our override and visit method invocation is one whose importance is both profound and subtle. So when you are using the visitor pattern, you are in control of traversal. The visitor pattern works by traversing through all of the nodes and edges in the graph that is the LST. And if you and so if you when you override a visit method do not yourself traverse into the sub elements of that method, they will not be visited. And so the most common way this happens is that the very first line in one of these visit method overrides is a call to the super method. And if we go and look at what this super method does, well, up to this level, we see that it is going through a method invocation and it's visiting, calling other visit methods on each of the individual pieces of this method invocation. It's visiting the white space. It's visiting the markers, which are just metadata, non-printing stuff. It's visiting the type expression. It's visiting the body of the method. It's visiting the name of the method. It's visiting the type of the method. It's visiting the arguments of the method. Each of the individual pieces it goes and visits. And so it's a very common question that I will see asked and answer in our OpenRewrite community Slack, which I invite all of you to join, is, I've written my visitor, but my LST element isn't being visited. Why is that? Why is it not doing what it is supposed to? And what you will often have is a situation like this, like they will have overridden, visit class declaration as well as visit method invocation. And in the containing element, they will have neglected to call the corresponding super method. So instead of doing, having this, they'll have, change some stuff and then return class decal. Right? They'll have done something like this. And so if I make this change, if I change nothing about, how we visit method invocations, but remove the traversal from visit class declaration, and I go back and we run our test again, we shall see that even though I did not do, didn't change anything about the processing and method invocations, that the recipe was expected to make a change, but made no changes. That I have broken this recipe such that it does nothing now. And that is because, I said, hey, when you find a class declaration, stop traversing. Don't go into it any further than that. And this being Java, all method invocations are contained inside of a class declaration in some form or another. So this method never got visited. Indeed, if I put a breakpoint here on the very first line of visit method invocation and run this under the debugger, we see that this breakpoint will never be hit. However, if I remove my broken override of visit class declaration and debug the method again, we'll see that traversal does make it to this method invocation. There we go. So now we've hit a breakpoint inside of visit method invocation, and we call super.visit method invocation so that a method invocation that was inside of another method invocation would still be visited, such as a method that called another method in its argument list. Pretty common way that method invocations might be nested within one another. Okay, and so then the very first thing we do after ensuring that the traversal of the method invocation still happens is engage in a bit of defensive programming. I was mentioning about the importance of earlier, where we use what we call a method matcher to check, hey, is this method one that I'm interested in manipulating? Even in a project with tons of assertions, assert equals invocations, there's going to be a bunch of other method invocations that are not assertions assert equals. So this method matcher is a utility that takes a string of the format fully qualified name of the class that the method is being called on, space name of the method, and argument list with 2 dots representing any number of arguments of any type. So we check, hey, is this method one we're interested in? And if not, we return early and we return it unmodified. And this is kind of a stylistic choice. You'll certainly see in recipes that I've authored and that most other OpenRewrite recipe authors have authored that we prefer to kind of return early rather than, obviously you could invert this and stick all of this stuff in here. And I should have cut rather than pasted if that's what I was going to do. but like some people and some coding style guides will say things like you should only ever have one return from your function. And that's fine. There's nothing wrong with that. But when you are programming in this defensive way, where you may have not just one or two, but like 5 or 6 criteria that you need to check before you're making any changes, you'd be starting off, if we were layering another couple if statements in here, you'd be starting off halfway, kind of halfway off your monitor if you kept on nesting like this. So I recommend that kind of early return style of rejecting things that you don't want to change one after the other in order to keep all of your recipe as easy to read as possible. Okay, anyway, so that style note aside, we continue on. We have found a method invocation that we are interested in making modifications to, and because we need to switch around, take the arguments of the old method and distribute them incidentally in reverse order to 2 new method calls, we're just going to get the argument list of that method invocation and just store it off to the side. And we don't need to worry about anything we call modifying this, because LST elements are immutable. We will not see anything directly changing the contents of an LST element, because we use these immutable data access patterns rather than, none of these LSTs will have set methods on them, for example. Now, if I say, m dot, there's an m dot get simple name, but there's no m dot set simple name. And that is, instead, you'd see an m dot, with name, right? Which doesn't, unlike a setter, doesn't mutate the object, but returns a new object with just that one field changed, and all of the other fields left exactly the same, which points to something important about how OpenRewrite works, in that it detects, because we're working with immutable data structures, referential equality can be used to detect mutation, or can be used to detect change, since we're explicitly not mutating something, right? So, when like visit method invocation returns the same instance that was passed into it, well, then you've like guaranteed that no change has happened. Yeah, and so if you did find a way to mutate an LST element, and there are some unsafe methods that would allow you to, and you made a change that did not was not reflected in a referential equality check, it could confuse things. So always use immutable data access patterns when operating on LSTs. Okay, so note about immutability done. Then we go ahead and call these maybe add import and maybe remove import functions, right? We saw that the test is obviously going to change the imports as appropriate, and these guys, it may seem a little strange that we're doing this now because we haven't actually changed anything yet, and it may seem even stranger that we move over, we called these functions, and I just told you that LST elements are immutable. And so like these must have some side effect, but nothing in here has changed. So what's going on? Well, if you were to look under the hood in these methods, what you'd see what they do is they schedule another visitor to run immediately after this one. And what these guys are going to do is, after the rest of the changes in this visitor are made, they will run and they will perform their functions. In this case, maybe add import is going to look and say, is there any symbol in this document whose type attribution says that it is an assert J assertion? If so, and only if so, it will add an import. Similar, so that it won't add an import if the recipe did not add some symbol that has this type. Similarly, maybe remove import is only going to remove the org.junit.jupyter.api.assertions import if it finds that there are no symbols remaining in the in this source file that have that type attribution. So this kind of points to maybe subtly an ethos of trying to be correct by default, right? Like we have all this information about what the types of symbols are, so use it to avoid making wrong changes. Okay, so with the import manipulation scheduled, if not actually completed yet, we're going to step into this block and store, the expected and actual arguments in convenient to access variables, and say, okay, we've gotten to this point. We've found a method invocation. It has the type we want. We have the data we want to keep from it. It's time to change it into its new replacement. And so Java template is a utility that we came up with to simplify the process of manipulating existing LST elements and producing whole new LST elements as necessary. Even though it's very tedious and error prone to create a new JDOT method invocation by hand, or even sometimes to use the with methods to modify it. In particular, you're likely to get the type attribution wrong if you were to attempt to do it by hand. And as human programmers, we're more familiar and comfortable with the text-based representation of code anyway. So here's where we provide a snippet of code that we want to have turned into an LST element for us, such that we can return it and have the change we want be made. And so, kind of under the hood, what Java template is going to do here is wrap this snippet in whatever additional text is necessary to make a valid Java source file. It's going to run that through the Java parser, turn it into LST elements, then reach in through that tree to get just the LST element representing the thing you're interested in, extract that out, give it back to you, and optionally interpolate in objects with optionally interpolate in other LST elements that into particular places. In this case, the arguments to these two functions. And so, since you know kind of how Java template works under the hood, well, you need to provide it with all of the things that the Java parser, the real Java compiler, would need in order to make sense of this Java source file, such as saying that, hey, this assertions is, we need an import for that assertions type. And even more importantly, or just as importantly, perhaps, we need to be producing, the Java parser that is going to be used to parse the source file that is generated around this snippet must be one that has assert jCore on the class path, because assert jCore is one that is what provides this assertion symbol. So if I were to go to my build.gradle or Maven POM for this project, I would have to see that assert jCore is taken as a dependency, so that this class path method here can look up assert jCore from the runtime class path of the recipe as it runs. And there's some alternative ways for bundling those in, but we don't need to get into all the details here. Okay, so and maybe to make this even a little bit more concrete, we can put a breakpoint here. There's this do before parse template function, which will show you, allow you to provide a lambda to operate on the Java source file that's going to be passed in to the Java parser. So if I go here and I look at the value of this template, we see that paste this into a Java Scratch file. We see that this is what we're actually going to be parsing from your template. And so we see that, yep, it has the import we specified. It has some, you don't really need to worry about these. These help to implement the placeholder logic to enable interpolation to happen. But like the kind of important thing is that this is a valid Java source file that contains the snippet you want, and some comments that help identify where the snippet you want is. And so this is what's going to be parsed when you call Java template, Java template.apply, and have just the bit you care about extracted back out. So if you're reporting to me like a bug with Java template, for example, include this, because that'll help me a lot in fixing whatever the bug is. Okay, so then the template is applied and the LST element is produced, and this cursor function is used while visiting an LST. There is a cursor which keeps track of where you are in that LST, or specifically what the parents of are the element you're visiting. So if I go in here and we hit this breakpoint again, we can look at what this cursor says. evaluate get cursor. Might be a little bit hard for you to see, but this cursor shows that this method invocation has a parent, and that parent is in this case some padding, but ultimately up to a block whose parent is a method declaration. The method declaration's parent, is a class declaration, or of the block, and then the class declaration, and then the compilation unit, and then the root. So, this is how you might like go find a sibling element or a parent element of the LST element you're visiting. But most of the time, you're just grabbing the cursor as is, and passing into some other function, which is going to make use of that context for a purpose. In the case of Java template, the purpose is to help produce this valid Java source file around your snippet. And then we provide a coordinate saying that we're going to replace the existing method invocation with the result of this template, and finally fill in the values, which should be swapped out for these kind of interpolation placeholders. And that is the recipe. And so if we allow it to continue executing, the recipe gets the job done, right? It makes these transformations and everything is happy and wonderful. And this itself performs, some tiny fraction of a migration to using JUnit or to use assert-J assertions. And so that is you should now feel well equipped to read this recipe and understand what's going on, or at least kind of understand what documents you would want to go look at to understand more. And in the kind of next session on Migration Engineering 2, we'll get into live coding a recipe like this from scratch, and we'll get into some more advanced challenges of recipe development, some more advanced features. There's stuff we haven't talked about today, like making data tables, which extract information from a recipe and put it into tabular data. We'll talk about recipes where you might use multiple visitors together to each solve subparts of a more complex problem. And generally, now that you understand all of the concepts and all the basics of working in this library, start putting them to use. So thank you all for attending. I hope this has been a valuable use of your time. I hope to see all of you in the OpenRewrite community Slack asking questions about recipe authoring and sharing bug reports and the like. And let me just put a join link in the Zoom chat so that anyone who's interested can join me there and ask your recipe authoring and execution questions. Until next time, I've been Sam. Thank you all so much for coming. Have a great day. Cheers.